Next will be the Peltier coefficient or Peltier effect. We use the Peltier coefficient uh, to describe um, these materials when you apply 1 unit of current density, how much the heat be adsorbed or released to the environment. We call this coefficient as a Peltier coefficient. And the detail would be explained in the following slide, but just remember that um, in that should be, if you want to measure the Peltier coefficient, should under the isothermal conditions. So what's the Peltier effect? And also what's the coefficient, Peltier coefficient? Based on the definition, when you apply the current density, 1 unit of current density, the heat, a heat flow be adsorbed or flow your materials flow through your materials, we call a Peltier coefficient of less materials. So what we have here is we have the N-type and P-type materials. In order to have a current passing through these materials, so we connect with a battery. So for example, like here, we have N-type materials and also connect with a battery. And on your right-hand side, we have a P-type of material also connect with a battery. Okay, so on your left-hand side here is a battery. So the current, the current is go through, this is anode. So we have a current passing through here, right? And because this is N-type, so the current passing through it go this way. So the major carrier of which is the electron will go this way, is upside direction of the current. So current go this way. So our electrons will go this way. And just remember, the electrons always carry the heat while you moves. So it turns out because the electrons carry heat, right? So which means that when the electrons move from the bottom to the top, it also lead or carry the heat. We will have a heat flow toward to the top. And the heat will come from where? Because the electrons carry heat, right? That which means that the heat would be adsorbed from this side, this junction. And the electron will carry heat to the other junction. So that will lead, you have a cold junction at the bottom and a hot junction at the top. So we have so the system absorb the heat from the surroundings and also deliver the heat to the surrounding as well. So you can absorb the heat, and this material just serve as a heat transporter and deliver the heat to the top. So this some kind of heater or cooler, because you cool this side down and heat this side up. So this can be a cooler. You cool this materials out. So you can put a Coke on this side. Then the Coke will be cooled down. And you also can put some water on this side. You can heat this water up. So the same idea for the P-type, but the major carrier becomes to the hose. But you also connect with a battery, so that also we just draw the current passing through these materials. The currents go this side. The major carrier will be the hose. So hose flow along this side or toward to the bottom, or also the hose. Each hose carry the heat. So the hose carry heat from top to the bottom side, which means that absorb the heat from the surroundings, and the hose carry the heat and deliver to the other side. That will lead this side, can cool this side down and heat this side up. Okay, so this is peltier effect, which means that you provide the current and you can absorb, you can, and this material will serve as a heat transporter, and you can cool one side down and heat the other side up. So the Peltier coefficient equals to, just remember, even you apply the same current passing through your materials, but how much heat be transported is the Peltier coefficient, because this heat is the heat, how much heat be transported through these materials. Okay, so people usually use this Peltier. So now you know each materials also have its own Peltier coefficient. But as you know that if you just have one materials, you can imagine that the heat flow is quite small. It's difficult for any applications. So usually when you visualize or you really want to use this electrical materials for Peltier effect, which means you connect to a battery or power supply. And for this Peltier applications, usually it's like in couples, use two materials in couples materials. The idea would be the same with Seebeck effect. And the practical applications here would be the cooler or the heat pump. Also assemble A material with B materials, and also use a battery as a power supply. And the material A and B are N-type materials. Okay, so also just write down the Peltier coefficient. And as you image that this is a battery, so I try to draw the current, the direction for the current flow. Let's go this way. And this and go this way, right? And this is a materials. So the major carrier, in order to analyze the direction of the heat flow, we need to know the directions of major carrier, but it's N-type. So the current go downward. So electrons will go upward, and electrons will carry the heat, right? So the heat will be JQA, will be upward. And for inside this material, because current go this way, and also it's unmaterial, so the electrons will go this way. So JQB will be go this way. And regarding to this regarding to this junction, we also probably will be absorb the heat here from the surroundings, right? So JQ plus JQB equals to JQA, because if you have a look on this junction O, the flux inside equals to the flux outside. So we got a JQ plus JQB equals to JQA. The same idea for this side. The electrons go this way. Oh, sorry, the current go this way, go upward. So electrons go outside. So let me draw. So the electrons go this way. It's JQB. And current go this way, and electron go this way. So JQA. So JQA plus JQ equals to JQB, right? Either way. So that will lead like JQ, because this plus this equals to this. So in order to write down what's JQ, it will be this JQA minus the JQB. So this is a Peltier coefficient. Let me switch back. Okay. So in order to write down the real like equations here, so the actually there are two driving forces coexist in these systems. One is a battery, which is J small or F small q electrical potential gradient, and the second one is we do have some heat flow, right? So I just write down the heat flux and the current density, and possible driving to have two driving forces here. So it's a corresponding F capital Q is negative temperature gradient divided by T, and F small q is a negative electrical potential gradient. Then due to that, that's the most important assumption here. We have constant temperature, which people also call it as isothermal conditions, which means that we do not have any temperature gradient along these materials. So this is quite important. So dt over dx equals to 0. So we can delete this term, and we can express the heat flow in terms of current density. So the heat flow equals to L capital Q small q divided by L small q current density. So based on here, we try to write down the Peltier coefficient. So for JQA, actually, you just put the A here, and this is material property, so you have the button A and current outside. So minus JQB is minus this B and current density, put it outside. So here, this is the upper part, and you directly divide by J small q, then you got a Peltier coefficient. So this is just directly divided this term with JQ, delete this term, so you have this minus this one. Let's just copy here. So Peltier coefficient can be written as this A minus this B. And if you take carefully here and combine with Osaka symmetry, capital Q small q equals to small q capital Q. So you can write down as SAB times T. Because why? Because L small q capital Q equals to dou ST. So this is ST, S, then put the, because S is a material property, so you have put the A, specific for material A, SAT minus SBT, and T put it outside. We have SA minus SB, so it's Seebeck SAB. So we got the Peltier coefficient equals to SAB times T. Okay, so if you have a larger SAB, then you will have a higher Peltier coefficient, which means that you got the higher performance for the cooler. So how to have a higher performance for this electrical, thermoelectrical cooler? You need to pick up the largest SAB, which means that SA minus SB should be largest. And one more thing is, don't forget that this is like we use A and B materials, combine them together, but each material also have its own Peltier coefficient equals to its Seebeck coefficient times the temperature. Don't forget that. And I also draw like other possible combinations for this um, like a Peltier effect. In your textbook, we just show you is in this case, we have N-type A combined with N-type B. But it's also possible have like a P-type A combined with P-type B. So I hope you can like try to draw this and write down the Peltier is corresponding Peltier coefficient. So if, for example, like it's P-type, so the heat flow will be along the current flow, so be downward. And this also downward. So you have downward, downward, right? And probably, and this is you focus on these junctions. So probably you have one heat flow inside, and probably there will be some heat flow. This side probably will absorb some heat inside. So you got JQ plus JQA equals to JQB. And some people probably will think about, okay, so this is, so we got the JQ plus JQA equals to JQB. And some people probably have like um, curious about if, Professor, if, is that possible? This is outside, in like show in orange is, yeah, if you switch A and B. So what this means, depending on the magnitude of JQA and JQB, if JQB is larger, you have a smaller, so you need to absorb more heat from surroundings. So the direction for absorbed from the surroundings or released to the surroundings will be depending on the magnitude of um, JQA and JQB. Um, So this is quite important.所以如果在这里的话，就是大家可能会想说，老师画这个是没有问题，那但这个在这个 junction 的地方，这个到底会是吸热还是放热，到底是怎么决定的？那其实决定在 JQA 跟 JQB 谁大。如果 JQA 比较它只有3的话，然后它是5的话，那就它一定是环境要吸热2，它才会2加3才会是5。但如果它比较大的话，然后它进来，然后变成2个，那它就会是 release。所以单看就是 JQA 跟 JQB 谁大，那 JQA 跟 JQB 谁大这件事情，就会跟它们 material property 有关，对吧？那我们来看一下，就是拥有最高的 performance 的组合，就是 P combined with N type of materials should have a highest performance for Peltier effect, right? So let's check why they have the largest one. Because it's current goalless side, and for N-type materials, the heat will go upside direction with of the upside direction versus the current, so will go upper. And this is P-type, so along with the current. And if you take a look on this junction, you have 2 heat flow outside, so not, for sure you need to absorb the heat inside from the surroundings, right? So you got the JQ equals to JQA plus JQB. So this will be half the largest one if you have the same current density passing through these materials. This combination will be largest because you have a JQA plus JQB, and the rest of one is JQA minus JQB. Okay, so this is the idea. Okay. Okay, so give you a quick summary. Now we already have introduced the both like coupling coefficients, and also know that Seebeck coefficient and Peltier coefficient. And based on here, you also know the coupling coefficient L small q capital Q equals to L capital Q small q, and that equals to rho ST. And Peltier coefficient is shown like this. Okay. So we're done with this one. So I'm going to give you a quick summary for these sections. Summary of flow process and coupling. A kinetics flow process must be driven by certain driving force. For sure, you have driving force. This driving force will cause the kinetics flow process. So don't forget, you need to determine how many driving force acting on your materials. Then you can formulate the corresponding flux. Then you also can solve the flux by continuity equations. Can be the mass conservation law in mass transport. Then use this to get the diffusion equation and solve it then by have a boundary and initial conditions. And finally, I hope you can get how the concentration of diffusion atoms changes with location and time. And also various kinetics parameters included the material properties, some kind of diffusivity, thermal conductivity, kappa, resistivity, seebeck coefficient, and so on were depending on direct and coupling coefficient. We proved that in previous slide. And also Ansaka symmetry is quite important. They assume that the systems is near equilibrium conditions. Under these situations, the L alpha beta equals to L beta alpha. Okay, so we finished the lecture 1, and in first part we tell you the difference between the thermodynamics and kinetics, and put more efforts to explain what is kinetics, how to and um, what's what are the driving force to determine what are factors can affect the kinetics process, which included the driving force and inertia of assistance. And in the meantime, you need to figure out in this your interesting kinetics process how many steps involved inside. If there's 2 or more steps, then you need to figure out the relationship between them. Are they in series or in parallel relationship? And don't forget to highlight the rate determining process. Then for second term, we define the equilibrium state and the steady state. And the difference actually is not the state, because both of them, the state function does not change with time for both cases. The only difference would be in steady state, we do have a constant driving force acting on these materials, and also it's an irreversible process. However, in other words, um, on the contrary, under the equilibrium condition, there's no driving force acting on it. And also, so that will be the big difference. And the third and fourth sections involve how to quantitatively describe the kinetics process. Then we introduce the beautiful equations, which is temperature times the sigma dot equals to the flux times the driving force. And depending on different materials kinetics process, we do have a different driving force and also its corresponding flux. But however, the system, if there are 2 or more driving force acting on these materials, in order to get the sigma dot, based on this like flux force equations, you also can uh, get the you also can have the formulate the flux times force in linear approximations. So that would lead you also summation the flux times the force together. Okay, so this is everything about the lecture 1. So the most important part to me is how to calculate the sigma dot in various systems. So first thing is you need to figure out how many driving force acting on these materials and what are they. As long as you know what are they, then you can also use the flux force relationship to know the flux. As long as you times them together, then you can, and also summation of them, and you can get a sigma dot. Okay. So this is if you have 2 driving force F capital Q and small q, then you need to remember that for heat flow, all the acting driving force will contribute the heat flow. And also for the current density, if there are 2 or more driving force, as long as you have driving force, that one for sure will contribute the flux. Okay, so this is the whole information for this coupling between the force and flux.